Hello everyone. On this video we will be going over tangents. Okay, so to kind of give you an idea of the tangents or derivative, let's say if we let x equals f of t and y equals g of t. Okay, just like with any parametric equation. Okay, so when the parameter is eliminated, we get rid of the t variable. So basically we're left with y equals some function of x, which we'll call f hat x. Okay, so now that we have those, suppose that function f, g, and our eliminated parameter f hat are differentiable. Okay, we can find the tangent line at a point on that curve. The tangent line at a point where y is differentiable. Okay, so now we're going to look at the parametric form of derivative. Okay, now the definition of this is if a curve that we'll call C, parametric curve C, is given by x equals f of t and y equals g of t, then the slope of the curve that we just called capital C at a particular point xy is dy dx, let me move that up a little bit, is equal to derivative of y with respect to t over derivative of derivative of x with respect to t. And that's assuming that derivative of x with respect to t does not equal 0. Okay, so let's kind of give this a look-see as far as visually, then we'll go into the proof. Okay, so if we have our x and y axis, move that up a little bit, and let's say if we have some curve somewhere that looks like that. Okay, so if we have any 2 points on that curve, let's say this point of our xy, this is our, instead of our x comma y, this is f of t, g of t, and this is f of t plus delta t, and g of t plus delta t. Okay, so that means from f of t to f of t plus delta t, that's your change in x. And from g of t to the point g of t plus delta t, that's your change in y. Okay, so we are going to use this along with the rules for limits to prove that the derivative of y with respect to x when t is your parameter is equal to dy dt over dx dt. All right, so I'm going to continue that on the next page. If you're writing, feel free to press pause, but we're going to go ahead and start our proof. Okay, so just like we pointed out on the previous page, we see that delta y, which is our change in y, is equal to g of t plus delta t minus g of t. Remember, you have your y2 minus y1. This is basically the same thing. Okay, and your delta x is equal to f of t plus delta t minus f of t. Okay, so you have your change in y and your change in x. Okay, now one thing we can notice here is that when delta t gets closer and closer to 0, because if it's equals 0, you have f of t minus f of t, which is just 0. You don't want that. But we can see that as this gets closer to 0, the delta x gets closer to 0. So as delta t gets smaller and smaller and smaller, these two get really close to being the same value. So since delta x approaches 0 as delta t approaches 0, using the limit formula, we can see the dy dx is equal to the limit delta y over delta x as delta x approaches 0. But we can easily replace that with the limit. Instead of delta y, we just have g of t plus delta t minus g of t all over f of t plus delta t minus f of t. And in this case, this is delta t approaches 0, because if that ever hits 0, you have a denominator, which is f of t minus f of t, which is 0, which you cannot have. Okay, we all know if the denominator ever hits 0, then you have chaos all over the world. Okay, so now what do? We're going to divide the numerator and denominator by delta t. Okay, so if we do that, we will end up with our dy dx equals the limit of g of t plus delta t minus g of t all over delta t over, and make that limit a little bit bigger since it should cover both. There we go. F of t plus delta t minus f of t all over delta t as delta t approaches 0. Okay, so now we can just get our limit itself and apply it to both the numerator and denominator. Because this one just applies to the whole thing. So that gives us dy dx equals the limit of g of t plus delta t minus g of t all over delta t as delta t approaches 0 over the limit of f of t plus delta t minus f of t all over delta t as delta t approaches 0. Now, this should look familiar because basically this is just the definition of a derivative. So your numerator here is just g prime of t, and your denominator is f prime of t. Okay, so looking at this now, where we are, we have dy dx equals g prime of t over f prime of t, and just kind of giving you an idea of where we're going from here. If you remember, that since y equals g of t and x equals f of t, and maybe put that underneath since I'm out of space. That means that g prime of t is just dy dt, and f prime of t is just dx dt. So really this just becomes dy dt over dx dt. Which is our formula. Okay, so now that we have proven the formula, good news is you do not have to go through all of this in order to use it. Okay, all you have to do is remember to find the first derivative, find the derivative of y with respect to t and x with respect to t. Okay, and we will have a few examples in a minute. Okay, but that's the end of this proof. So we're going to go ahead and go to our next, I guess you could say, formula. So if you're still writing, feel free to press pause, but we're going to go ahead and move on. Okay, so now we're going to look at horizontal tangents. Okay, now if you remember a horizontal tangent, that just means that your slope is equal to 0. Okay, and we all know if your slope is equal to 0, that's just another way of saying your first derivative is equal to 0. All right, so to break that down as far as parametric equations, to get a horizontal tangent, you have dy dx equals dy dt over dx dt. And this has to equal 0. Okay, so for this to equal 0, that just means your numerator has to equal 0, because 0 divided by anything, any non-zero value is 0. Okay, so that just means that dy dt equals 0, but your denominator cannot equal 0. Okay, so to find the horizontal tangent, just find the values where your numerator is equal to 0, but not the denominator. All right, how about we now look at your vertical tangent? Your vertical tangent is just when your slope is undefined. Okay, so when your slope is undefined, it really just means you have a denominator of 0. So that means that your dy dx, which again is dy over dt over dx over dt, in this case, your dy dt will not equal 0, but your dx dt will equal 0. Okay, so the horizontal tangent and vertical tangent uses the same formula, but they kind of swap which one can equal 0 and which one cannot. All right. Now we have one more before we start jumping into our examples, and that's the second derivative. Of a parametric equation. Okay. Now, before we show the second derivative, we know that dy dx, or your first derivative, we can actually rewrite that as the derivative with respect to x of y. And also, using the chain rule, d dx, we can write that as derivative of t with respect to x times the derivative with respect to t, or vice versa. Okay, so both of these will play a very big role in pointing out the second derivative. All right, so let's look at our second derivative. Let me kind of separate that. Second derivative of y with respect to x. The same way we did this here, we're going to make that equal the derivative with respect to x of dy dx. Okay, so you get your first derivative, and then you get the derivative after that. Okay, we see here our derivative with respect to x. We can rewrite that. So that will be derivative of t with respect to x times derivative with respect to t of dy dx. Okay. Now, if we multiply this by dx dt over dx dt, these two will actually cancel out. It's kind of undo each other. So we end up with second derivative with respect to x, move that up a little bit, is equal to derivative with respect to t of dy dx all over dx dt. And the second derivative, just like in Calc 1, this would be very helpful to find concavity. Okay, so whether it's concave up or concave down, this is very helpful for that. All right, so hopefully this made sense. So now let's jump into our examples. Okay, so if you're still writing, feel free to press pause, but we're going to go ahead and get started. Okay, so let's say, for example, we want to find dy dx, first derivative. We want to find our second derivative. Then we want to find the slope and concavity. And with this one, that's if possible. Because not every question will be able to have the concavity found at the indicated value. Okay, so starting off, say we have problem A. So we have x equals 2t, y equals 3t minus 1, at the point t equals 3. Okay, so for problem B, we make it a little trickier. So x equals 2 cosine theta. Y equals 2 sine of theta at the point theta equals pi over 4. Okay, so for all of these, we want to find first derivative, second derivative, the slope, and concavity at the specified values. Okay, so let's go ahead and get started on problem A. Move this up a little bit. Okay, so for problem A, we know that dy dx is equal to dy dt over dx dt. So we're going to go ahead and work this out right over here. So we know that y is equal to 3t minus 1. So that means derivative of y with respect to t is equal to 3. And we know that x is equal to 2t. So dx dt is equal to 2. So that's equal to dy dt is 3 and dx dt is 2. Let me get me some pencil lead here. There we go. So that means that dy dx is equal to 3 over 2. Okay, so what about our second derivative? Our second derivative, that's derivative with respect to t of our dy dx over our dx dt. Okay, so that's going to equal the derivative with respect to t of our dy dx, which is 3 over 2, over dx dt, which is 2. Now the derivative of a constant is equal to 0. So that just becomes 0 over 2, which is 0. Okay, so whenever your second derivative is equal to 0, we'll move that up a little. That means it's neither concave up or concave down. Okay, now with this one, you can't find the slope at the specified value because there is no t to plug that 3 into. Okay, so this is it for this particular problem. Okay. And we're going to do B on the next page because what I want to do is just put a little note at the bottom of this one. If your second derivative is greater than 0, then it's concave up. If your second derivative is less than 0, then it's concave down. And if your second derivative is equal to 0, as you can see up here, it's neither. Okay, so just a refresher in case you don't remember it from Calc 1. Could have been a while, so that's not too unheard of forget it a little bit. Okay, so we're going to go ahead and continue and do B on the next page. So if you are still writing, feel free to press pause. But we're going to go ahead. All right, so for problem B, remember we have y equals 2 sine of theta. And x equals 2 cosine of theta. Okay. Now notice this one does not have a t in it. It has a theta. So instead of dy dt, we're going to have dy d theta. Nothing else changes. We do the exact same thing as far as finding our derivative, just that instead of t, our parameter is theta. Okay, so derivative of 2 sine theta is 2 cosine theta. And the derivative of 2 cosine theta, since cosine, derivative of cosine is negative sine, that's negative 2 sine theta. All right, so that means we kind of separate that a little bit. Your dy dx, which is derivative of y with respect to theta over derivative of x with respect to theta. Dy d theta is 2 cosine theta. And dx d theta is negative 2 sine theta. The 2's cancel each other out, so you're left with negative 1. So that's negative. And cosine over sine is actually cotangent. Okay, so your dy dx is equal to negative cotangent theta. All right, so how about we go to our second derivative, which is the derivative with respect to theta of your dy dx over dx d theta. So that means you have the derivative with respect to theta of your dy dx. Remember, it's just negative cosine, no, cotangent theta over dx d theta. All right. Okay, so really that simplifies derivative with respect to theta of negative cotangent theta. What I'll do is I'll make a little note here so you can kind of follow where we're going. So derivative with respect to theta of cotangent, we'll do the negative in a second. That is just negative cosecant squared theta. Okay, so if we have negative cosecant, if we factor out the negative 1, and we have negative cosecant squared theta, then what we're left with is positive cosecant squared theta over, let me kind of block that a little. It's a little closer than I would have preferred. Let me move that down a little so it's not confusing anyone. Okay, so equal to put my 2 in the wrong spot. Cosecant squared theta over dx d theta. Remember that's negative 2 sine theta. Okay, so you can look at it this way. Let me kind of block this off. So for this one, remember 1 over sine is cosecant. So really this is cosecant squared times cosecant, which is cosecant to the third power. So you have -1/2 times cosecant to the third. Okay, so this is your second derivative. Okay, so we have a little bit further to go because now we're going to plug in our given value. Okay, so move that right on up. So that's theta equals pi over 4 dy dx equals negative cotangent of pi over 4. Cotangent of pi over 4 is 1, so this is just -1. So this is your slope at theta equals pi over 4. Okay, so now we go ahead to our second derivative and we plug it in. Which is -1/2 cosecant cubed pi over 4. Okay, now if you wanted to, you could just rewrite this as -1/2 times cosecant pi over 4 to the third power. Okay, so cosecant of pi over 4 is square root of 2. So that's -1/2 times square root of 2 to the third power. Okay, so square root of 2 times square root of 2 is 2. So those two would cancel out, which leaves another square root of 2. So let me go ahead and write that out. So you have -1/2 times square root of 2 times square root of 2 times square root of 2. Okay, so you multiply these two together, you get 2. Let me put that up top. Okay, so 2 times 1/2 is just negative. Well, -1/2 is -1. So that leaves you with -1 times square root of 2 is negative square root of 2. Okay, so your second derivative is equal to negative square root of 2. So because the second derivative is negative, we know it's concave downward. Okay, so it's at that point, it's going to look like that. All right, so hopefully that made a little bit of sense. If you're still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Okay, so for example, we want to find dy dx and your second derivative for x equals t squared plus 1, y equals e to the power of t minus 1. And also find which values of t is the curve concave upwards. Okay, so what I want you to do is I want you to press pause and try to solve this one on your own. All Alright, so I'm assuming you've already pressed pause and you've worked on this already. So let's just go ahead and verify your answer. Okay, so dy dx, we know that's equal to, since we have a t and not a theta on this one, dy dt over dx dt. Oh, excuse the shadow here, depending on which time of day I make the video. You can get a little bit of shadow from the camera and the sunlight. Okay, so we know that x is equal to t squared plus 1. So dx dt is equal to 2t. Probably should have put that on the bottom just to match that, but no big deal. And y is equal to e to the power of t minus 1. So dy dt is equal to e to the power of t. Okay, so that means your dy dx will equal dy dt, just here. Remember not to mix those up. So that's e to the power of t over your dx dt, which is 2t. Okay, so that's your dy dx. Now, you're going to find your second derivative. Move that up a little. There we go. And that is d dt, derivative with respect to t, over your dy dx over dx dt. So that comes down to your derivative with respect to t of your dy dt, which is e to the t over 2t, over your dx dt, I meant to point there, which is 2t. Okay, so now the denominator, we can use the quotient rule for derivatives. So you have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared, and that's all over 2t. Okay, so we have our derivative here, and that's all over the 2t. Don't forget that 2t because that's important. Okay, so if we go ahead and simplify this, we have this 2t squared and multiply it by that 2t. That's going to equal 2t e to the t minus 2 e to the t all over 2t cubed. Move that up a little bit. So if we decide to factor out the 2et, it leaves us with t minus 1 all over 8t to the third. So if we simplify the 2 and the 8, that should be dx squared. Kind of got mixed up there. My apologies for that one. That should equal e to the t times t minus 1 all over 4t cubed. Okay, so we still have a little bit of work to do, and we're running out of room on this sheet. So I'm going to continue this on the next sheet. So if you are still writing, please feel free to press pause. But we're going to go ahead and go to our next. Well, continue solving this one, really. Okay, because we're going to find which values of t is the curve concave up. All right. Okay, so we know the curve is concave up when the second derivative is greater than 0. Okay, so we know that. So that means that our second derivative, which is e to the power of t times t minus 1 over 4t cubed, has to be greater than 0. Okay, well, when will that be greater than 0? E to the power of t is always positive, so we don't have to worry about that. But that just means either e to the power of t, t minus 1, and 4t cubed are both positive or both negative. Okay, because remember, positive divided by positive is positive, negative divided by negative is positive. So they have to be either both positive or both negative. Okay, so let's go ahead and figure that out. What about our numerator? E to the power of t, t minus 1, when is that greater than 0? Okay, that's greater than 0 when t minus 1 would have to be greater than 0, which means t is greater than 1. Okay, so that would be positive as long as t is bigger than 1. And this denominator has to be greater than 0. 4t to the third is greater than 0 when, I'll put this, t is greater than 0. Okay, we divide both sides by 4 and just cube root both sides, we get 0. Okay, now what about, this is when both are positive. Now what about when both are negative? E to t times t minus 1 is less than 0. When is it less than 0? Well, that's when t itself is less than 0. Remember, it's not less than or equal to, so you can't have it equal to 0. But if it's less than 0, this would be a negative number. And 4t cubed is less than 0 when t is less than 0. Okay, so for this to be positive, it has to be greater than 1 and greater than 0, so we can just say it just has to be greater than 1. Okay, and for this to be negative, they have to both be less than 0 or less than 0. So we know that the second derivative itself is greater than 0 when either t is greater than 1 or t is less than 0. That's when it's concave up. All right. So hopefully this made sense to you, and I will see you on the next video.